So today we're going to do special functions. I'm going to have to slow down today. You're going to want me to. And try to be very deliberate in this. Special functions, or piecewise functions particularly, is just something we're kind of not prepared for a lot. We should be, but it's brand new, like really kind of unique stuff for us mathematically. So we're going to write and graph piecewise defined functions, and we're also going to look at step graphs and absolute value functions. A piecewise function is a function that is written using two or more expressions. That's why it's in pieces, because you're doing two, usually three different pieces, different expressions, different pieces. The step function is a function whose graph is a series of line segments. It'll kind of look like steps. That's why we call it the step function. And it's a realistic function utilized in our world for a variety of things, including something like hourly rates at a garage or in a psychiatrist's office or something of that nature. And then we may spend a little bit of time looking at greatest integer, although I think the first two are our primary focus. So, generic, graph, y equal 2x plus 3. If I have you to graph that, if I ask you to graph that and just graph it, then hopefully you know that the intercept's at 3, the slope is 2, rise 2, run 1, rise 2, run 1, rise 2, run 1. So basically we get this graph. May not be perfect, but it's close, right? Get this graph. Now down here at the bottom it says, what if the domain is limited to non-negatives? So I'm coming back to here. What if the domain is limited to non-negatives? In other words, x can't be a negative 3. It can't, that's a negative 4. It can't be a negative 3. It can't be negative 1. Well, if it can't be those things, then the graph can't exist there. So these things do not belong. Non-negative. Can it be 0 if it's non-negative? Yes. And so this is the graph of this equation with this parameter, this specific limitation, okay? So that begins to peek into the window of what a piecewise function might do, is we saw what the graph would have been, but then somebody says, oh, but they can't be negative. X can't be negative. The domain is what we said. And so we start to see how the effect may be. So I got the same graph. Oh, wait a minute. Yeah, that's where I want to go. So I've got the same graph. I'm going to graph it. Oops. Let me get my color one back out here. So y-intercepts at 3, rise 2, run 1, rise 2, run 1, rise 2, run 1. And basically this is my graph. May not be beautiful, but it works. Well, what if we said the domain is limited to the negatives? It can only be negative. It can't be positive. The domain can't be positive. Then we can't have where x is 2, and we can't have where x is 1, and where x is 4, and where x is 2.5. Those things cannot exist. It can only be, what's now? It can only be a negative number. So guess what 0 is not? 0 is not a negative number. So it can't even be 0. X can't be 0. So 0, 3 is not on the graph if we have that limitation of the domain only being negatives. So we had the whole graph, but then we realized, well, this part can't exist, doesn't exist. And we have lots of limitations in various things we do mathematically, algebraically, in real world problem sets. You know, like we know that Bobby can't be a negative 11 years old, so that would be a limitation. He can't be negative anything years old, so that'd be a limitation on the graph that we were making of some situation about Bobby's age, and so on. Those are things that we have that limit us. I think I showed you this before, but if you have some person standing up, you know, like in the football stadium, and they throw a football, and the football is gonna go up in the air and then down to the ground. Well, that's kind of part of a parabola, right? It's part of a parabola. But that's an unrealistic parabola, because you can't have the land before thrown, you can't have the time before the ball was thrown, nor can you have the ball going into the ground. So there are limitations on that we would look at in a piecewise function situation. I've got too many. Yeah. So one more of these. So I'm going to go back to the same graph. I've got that, rise 2, run 1, rise 2, run 1. So I start with my intercept, and I'm going to graph. And then this time my limitation is, what if the domain is limited to x greater than 3? So right here is where x is 3. So in other words, it can only happen from here over. I don't have a whole lot to work with there. But I'll show it to you just the same. So these things can't occur. They can't occur. None of them. In fact, since x has to be greater than 3, 3 can't even occur. And so really that should have been, you know, kind of like that. But that's what we're talking about as far as the introduction to piecewise functions. Now, let me erase these pieces here. So here we've been given a situation where you have these two, see the parentheses or the set bracket, these two situations. One is when x is less than or equal to -2. The other is when x is greater than -2. So let's begin this by graphing. I'll do it in blue. Let's graph that first function. So we start at 2, slope is 1/2. So just rising 1, running 2, and that would be the graph of that equation of that function. But they tell us, oh, but it only exists when x is -2 and below. So in other words, none of this is there. Doesn't exist. Then this one says y is 3. Now you may or may not know, but y is 3 is here. It is a horizontal line where y is 3. Up 3, up 3, up 3, up 3, all the way up 3 every time. But they tell us, oh wait, but it only exists when x is greater than -2. So we're going to have an open circle on that and erase this part because it only occurs from here over. Nice. So graph this. Graph this. I'll check that one off in red. That's y equal, or f of x equal, x minus 1. So -1, and our slope is 1. So you can see how this is going to work pretty easily. And so this is the graph of this function. But they said, well, wait a minute. It can only happen when x is less or equal to 3. So here's where x is 3. So it only happened from here over, which means this doesn't exist. It can only happen from here over, right? Like if you're looking at the number line, it can only happen from here over. So that's a restriction. Next, I'll do this one. And it says f of x is -1 or y is -1. That occurs here. But it says, wait a minute, it only happens from here over. So that's from here over, but it doesn't include here, so I have open circle. And then I'm not going to be able to erase it all exactly cutefully, but you'll get the picture. It can only happen when x is 3 or bigger. Actually, it can't happen when 3. That's why it's open circle. Piecewise functions, that's how they work. So you can see their picture. First piece, and adding the second piece, it looks like ours, of course. And they got their answer, and it looks like ours. So this would be a good time for you to pause the video and try for yourself. This one, intercepts at 1, slope is 2. Rise 2, run 1. That would be the whole graph, but we're limited where x is -1. So from right here, greater than goes in that direction. So this part of the graph gets lost. This one is -3. Y is -3. That's what that says. But they say, well, wait a minute. It only happens from here over, right? Less than or equal to, from here over. So that means we lose all of this much of the graph because it only starts where x is -1 and goes over. It's the same picture we just got, right? It says identify the domain and range. So that's a good question for us to look at here. Remember, domain is values of x, range is values of y. So domain is any x. Like it could be -10, -5, -7, -2. It can be -1 here, not here, but here. X is -1 here. And it could be positive and so on. It could be anything. X can be anything. Now the range, that's different. The range is the values of y. And you can see it can be nothing down here. They don't exist down here. No y values down here. No graph down here at all, period. Then you got a blip on the radar at 3, -3. And then you got a gap. And then it starts back right above -1. And you got all kinds of possibilities. Who says that? Who says that? This does. This says y can be -3, or it can be bigger than -1, and that's what we saw. Answer is C. Now, if you didn't get that, you might want to go back, back the video up, listen to what I said again, see if you can see it. Now, this is maybe the harder part. For some students, it's definitely the harder part, because now they've given us a piecewise graph and said, you write the function. So that's why we started off with the first part where we had the function, we had to graph it. But now we've given the graph, we have to draw or write the function. So I'm gonna try to lead you through this a little bit at a time. So we're gonna call ours f of x, and we're gonna say equal. Let's talk about this graph first. This graph. This graph is y = 1. Now you should know that. You should know that. Horizontal and vertical, horizontal's y, vertical's x equal. You should know that. It's not because you memorized it, but you can see every point has a y of 1 in this problem. The x can change. It can be 2, it can be 3, it can be 3.5, whatever. But the y is up 1, up 1, up 1, up 1. So y is 1. So that's what we're going to say. F of x equal 1 for, where's it start at? X is, where's it start at? X is 2. I said 2 and I wrote 3. Oh, I don't know why. But it could be equal, right? Because we get the closed circle. Get the closed circle. Okay? Now let's look at this one. This one. Normally this goes on and on and on. It just does it in this case. But normally it's a line that goes on and on and on. I do observe that the b is -4. Did you see the b is -4? The y-intercept is at -4. And I also noticed that the slope is 1. Rise 1, run 1, rise 1, run 1. So that is y equal x minus 4. Agreed? So f of x equal x minus 4 for x less than 2, right? Starts at 2, but it's not 2, it's just open on the 2, that's why we don't have the equal part, but it's when x is less than 4, or less than 2, that happens. That's our answer. They've done some similar dancing, and you can see what they got there. Their notation looks different than mine. I kind of like theirs better now that I see it. I'm always conflicted on which way to do that. Okay, identify the piecewise function here. Well, would you agree that this is y equals 7 up here? So that's y equals 7, that's y equals 7, that's y equals 7, that's y equals 7. They all have that. Who has the right criteria? Well, y equals 7 occurs when x is -4 or bigger, because it could be equal, right? -4 or bigger. So that says +4 or bigger. So no. That says bigger than 4. No. That says less than or equal to 4. No. That says greater than or equal to -4. Yes. It must be the D answer, and I haven't even done the other piece. I could then go do the other piece just to be sure that that works. You know, the slope is 2. You can see that. Starts at -4, doesn't include the -4. Answer is D. All right. So here's where we'll finish up. One psychologist charges for counseling sessions at the rate of $85 per hour or any fraction thereof. One psychologist charges for counseling sessions at a rate of $85 per hour or any fraction thereof. I just want to make this point with you. So if you go, and let's talk about this in terms of minutes, thinking of hours. If you go and stay 50 minutes, it costs $85. If you go and stay 60 minutes, it costs $85. If you go and stay 61 minutes, it costs $170. Because $85 per hour, any fraction thereof. So if you go a minute over, it costs you another $85. You might as well stay for another 59 minutes. You know, it's kind of how that would work. And you wouldn't remember this, but in the old days, that's kind of how cell phones were. Cell phones was based on a minute per minute charge. And if you talk for a minute and 59 seconds, it cost you a certain amount of money. If you talk 2 more seconds, then that was 2 minutes and 1 second, and you had to pay for another minute. And so people were always kind of trying to monitor their phone time because they wanted to make sure they got that thing shut down at the right moment. So looking at that then, this is going to be a step function. So you can see what I said about the 170 if it's 2 hours or less than 2 hours, as long as it's more than 1 hour. So between 1 and 2 hours, it's $170. And so they developed this little X and Y thing that says anywhere from 0 to 1 hour is $85, anywhere from 1 to 2 hours is $170, and so on. Notice the not equal part here and the equal part here, because if you do equal 0, you don't pay anything because you didn't go and you didn't spend any time and you don't pay a dime. That's good. So that makes sense. And then all the way up to 1 hour, 60 minutes, still just costs you the 85, right? Including right at 60, just costs you $85. But 60 minutes and 30 seconds, you're going to have to you're going to have to pay the 2 hour charge. So that's $170. Anything over the 1 hour, you get to pay the next charge up, the up charge. And so, oops, wrong way. Nope, that was the right way. So you can see what that looks like. And it looks like, and it is, a step function. So it looks like you're going up steps. So you can see no money at the 0 minutes, but right past the 0, 1 minute in, you're paying $85 all the way up to 60 minutes or 1 hour. And then you bounce up to here. But at 1 hour, you're really here. But right past that 1 hour, you gotta go, and that's how that would work. And that's the picture, and that's the step function. And those are pretty familiar. The daily grind charges $1.25 per pound of meat or any fraction thereof, which is kind of weird. So if you get a pound, you pay $1.25. If you get a pound and an ounce, you gotta pay $2.50. If you get a pound and 15 ounces, you still just pay $2.50. So, you know, get your stuff if you can. But you can see the step functions. That one I've got marked out because it's a linear function. Well, no, it's going to be a step function. And so you can see the one that fits here is the A, because it says no money, right, for no time. But right past that, you pay $1.25 all the way up to a pound. Then when you jump up to another pound, it costs you $2.50 and so on. So the answer is A. All right, parent function of absolute value functions. Absolute value functions is something we're going to use a lot. We talked about absolute value in the past, previous courses, and even in elementary school we talked about absolute value, but thinking about the graph of it. The graph of it looks like a V. Looks like a V. Type of graph is V-shaped. Domain is all reals. You can put any number you want to, positive, negative, rational, irrational, it doesn't make any difference. You put any number you want to in there, and take the absolute value of it, because absolute value is just distance from zero, and they all have a distance from zero. The range is all non-negative real numbers, because you can see it comes down to the x-axis and goes back up, touches here at the origin and goes back up. And this is the parent function, because the kids are going to look a little different. And really it's a piecewise function, but we don't typically think of it that way, because you got the possibility of x being a positive, x being a negative, or x being equal to zero. All those things can happen. Remember the case 1, case 2 kind of stuff? That's hidden in there somewhere. The intercepts are both at 0 at the origin, and it's not defined for anything below 0. Y can't be below 0. Now, the parent function we just said was here. Oh goodness, I didn't mean to do that. All right. So the parent function we said was here. I just want to re-note that, because I want you to see the parent and the kid together. So I'm going to do stuff like -2, -1, 0, 1, 2. So if I put -2 in here, I get 2 plus 1 is 3. If I put -1 in here, I get 1 plus 1 is 2. Put 0 in here, I get 0 plus 1 is 1. Put 1 in here, I get 1 plus 1 is 2. Put 2 in here, I get 3. And so when I graph that, I got -2, 3. I got -1, 2. I got 0, 1. I got 1, 2. I got 2, 3. So do you agree that the parent and the kid look a lot alike? They look a lot alike. They look a lot alike. Not much different. They're both V-shaped. The domain's the same. The range changes just a little bit. It bumps up 1, and you would have to say that y is greater than or equal to 1, whereas this one, the parent, it was y greater than or equal to 0. The range, what things it could be. So it changed just a tweak. Both of them, as I said, the domains were the same. So they did their T-chart here. They did their graph. They didn't put the parent on there, but they do have the same domain and range that we just had. Identify the function shown by the graph. You just have to kind of take and do T-charts and plot points and see what this is, and it is B. You say, how'd you know that? Well, because I've done a few of these. It is B. But if we take this and do a T-chart, and we do, like, here's our X and our Y, let's do -2, -1, 0, 1, 2, just because we can. So we put -2 in here, get -3, which is +3, which is 2. Put -1, get -2, which is +2, -1. Put 0 in there, be -1, which is 1, -1. It's a 0. Put 1 in there, you get 0, -1. You put 2 in there, you get 1, -1. And so if I graph those, have -2, 2, -1, 1, 0, 0, 1, -1, 2, 1, you can see how they fit. You would not having the luxury of being able to zero in on that or zone in on that, you may have to do some other things. Later, though, we will talk about the trick that I used in my own mind for that problem.